Let us now go over our considerations about motional EMF and what it can teach us actually about additional facts regarding Maxwell's equations. In particular, this idea that a changing magnetic field can induce an electric field. We were talking about a thought experiment. Here I'm giving you just a slightly different version of it. And in this thought experiment, there are two different ways we can operate. In one way, we take a circular circuit where I've got a resistor and a conducting wire that's moving through a magnetic field. And I take this loop and I move it at velocity v off to the right in a stationary magnetic field. There's a series of effects which occur, and the final bottom line is that a current is driven through the circuit due to the magnetic forces on the particles in the moving wires. We can carry out the corresponding experiment that would correspond within relativity, namely we change our reference frame so that now it is not the circuit that's moving. We go into the circuit's reference frame. In this case, what we have is the same exact circuit, but now the circuit is stationary, and while that circuit is stationary, the magnetic field, the source of that magnetic field, is actually being dragged then here off to the left. And what I would like to do is to compare our analyses of these two situations and line things up very carefully so that then we can understand how we would need to adjust Maxwell's equations for the case of the changing magnetic field and the stationary circuit, to be able to account for that. Because we know the net effect in both cases has to be the same, that exactly the same amount of current I has to be driven through the external resistor. So if we look carefully at our analysis and the Maxwell's equation that pertains in the first case, in the case of this motional EMF, we can begin by looking at the voltages as we go in a loop here around our circuit. So I'll start here at location X. So if we wanted to add up those voltages, of course, mathematically what we're doing is we're looking at minus the path integral around that loop of the electric field dot dl. And we know that when we do that all the way around this loop, through these wires and through the moving wire over here, the conductor, the perfect conductor, and over here through the resistor, that we're doing really nothing other than adding up the changes or adding up the voltages as we go around that loop. Now, in this case, what we find is that, say I start at location X, I go through my resistor along the direction of the current flow, so we know what that will give us. That will give us minus I times R, a drop because we are going with the flow downstream through that resistor. Then what we do is we pick up the voltage that takes us from point A through here to point B, the minus to plus change through this wire that is moving throughout the magnetic field, and we have a very specific exact result for that. We called that result the motional EMF. And we had a formula which actually gave us that motional EMF. The point of writing it this way is to realize that it doesn't have to be just this simple particular system that we had addressed previously in our specific example. It could be any wire loop doing any kind of motion throughout that magnetic field. No matter what the type of motion is, what we had derived previously was that that motional EMF is going to equal exactly minus the time derivative of the magnetic flux through the loop. Now, in this particular case, we also know that going through our circuit like this, because there's nothing unusual going on, there's no changing magnetic fields here that we might expect might change Maxwell's equations for us. The way we determine the current here was just by naturally setting the sum of these voltages actually equal to 0, and then from that consideration we are actually able to solve to determine the current, and we can see then that the current I would equal the motional EMF divided by R. Now, when I look at the value of the motional EMF, what we notice is that it's equal to minus the derivative of the magnetic flux with respect to time in this particular situation. And what we'll also notice is that that EMF has a specific value that has to be sort of the same between these two situations, because the EMF is actually the current I times R, And we do expect that at the end of the day, because of the relativistic equivalence between the two different situations, it's going to be exactly the same amount of current that's going to be flowing through our external resistor. So that's the summary of the situation in the motional EMF case. For the case of this induced electric field, we have a similar but slightly different set of considerations to go through. Once again, in this case, we can go ahead and calculate the closed line integral of E dot dl around our path. And in this case, things are going to be the same but slightly different. This again amounts to a sum of voltage changes or contributions to that line integral as I go around my path. Once again, if I start down here and go counterclockwise through my circuit, in this particular case, again, as I go through my resistor, that's going to be a drop in potential, a negative voltage going downstream with the resistor. So the beginning parts of this are the same. I get minus IR. And then when I get to the remaining portions that take me from this A, this minus terminal, and B, this plus terminal as we had before, now I'm going through a perfect conductor. I imagine these to be perfect conductors on this side. It is only this material that has the resistance. I'm going through a perfect, now stationary conductor. In contrast to the upper situation, where I have a conductor that's moving through a magnetic field, so the equilibrium electric field inside of there is not zero, but in fact has a particular value. In contrast to that situation, I now have a conductor which is traveling at zero velocity. So from our previous considerations, we realize that the electric field remains zero here inside this conductor. So as I go all the way around this loop from A to B, I actually pick up zero voltage change going around my loop. So now things seem to be a little different from how we had them before, right? This path integral of E dot dl no longer seems to be zero. It's equal to minus IR. In fact, in the diagram you can see it. There's a contribution from the resistor. I'm going to get an electric field integral contribution here as I go around my loop, but nothing over here. I'm not going to get zero. In fact, you can see how in the motional EMF case, things are set up so that I get zero. I get a positive E dot dl on this side, and then on this side, because of the induced electric field in the conductor, I get a negative contribution, so we can see we would get zero in this case. But in our induced E field case, we can see we are not getting zero. We're getting minus I times R, where that is the current flowing through this external resistance that I've attached to some loop of a perfect conductor that's moving somehow arbitrarily through this magnetic field. Now we can also get a little more specific about this because we know that the current in the two situations is the same, and we also know what IR equaled in this previous situation. In the previous situation, IR equaled just minus the time derivative of the magnetic flux. So minus IR is going to actually equal then the time derivative of that magnetic flux. And so now we see that in the case of a stationary loop and a changing magnetic field, we have a very interesting situation where the integral of E dot dl around my pathway for the two situations to be completely equivalent has to equal minus the time derivative of the magnetic flux through my loop. And so that's a new result. No longer is integral of E dot dl zero, but it has a very specific value that's then tied to the time derivative of the magnetic flux through the loop around I'm integrating E dot dl. So now we're in a position to upgrade Maxwell's equations. So here are the equations as we'd written them down the last time. We've got our Lorentz force law, our Gauss's laws, which are now very well established, our last discussion was looking at the analogs between Ampere's law and what looks kind of like an electric field version of Ampere's law. We would expect, by symmetry of the two fields, that the first term should be the flow. Here, magnetic field loop integral depends upon the flow of electric charges. Here we would expect electric field integral would then depend on the flow of magnetic charges, but there are no magnetic monopoles, so we expect that the analog of this term would be 0, and of course the analog of the current density also would be 0. It's this next term now that suddenly we see has appeared for us. The integral of E dot dl should involve something else, we might guess, some set of constants times the time derivative of the flux. In the magnetic field case, it's the changes in the electric flux. So in the electric field case, we would expect that it's changes in the magnetic flux. So the equation that we just found actually gives us what this additional term here must be. We see integral E dot dl should be minus the time derivative of the magnetic flux. So now we know which constants go in front. It's not plus mu naught epsilon naught. It's just a simple minus sign and then the time derivative of the magnetic flux. And similarly, when we look at the differential equations and we see how they line up, we know that we generated this integral equation by simply integrating the differential equation. And the way we can generate a flux term with a prefactor is to simply have the same prefactor in the differential equation, so a minus sign, and then just the partial time derivative of the corresponding field. So that would be the partial time derivative of the magnetic field is what would go here on the electric field case. So this modified path integral result for the electric field that includes in particular these changing flux terms, this full law now has a name. This is known as Faraday's law. And not only then do we have a new law and a new term in Maxwell's equations, but at this point we have now completed all of electromagnetic theory. There are no additional equations, and we can see the beauty of the symmetry between the fields and how the various terms align with one another, and all of these equations then determine for us the values of the fields, all ultimately through local interactions and differential equations. So there's no action at a distance in how the fields get determined, and moreover, when we look at the forces on particles, we can calculate those from the fields, again, in a local fashion. So we've resolved all of the problems of action at a distance. And what we have now is a truly relativistically invariant theory of fields, from which now we can derive further ultimate consequences of electromagnetic theory.